In this lesson, which is another part of our enterprise data center integration module, we are going to talk about data center interconnections. Cisco usually recommends that we isolate and reduce our layer 2 network to the smallest possible footprint, right? And we try to isolate that at a minimum to the access layer. Server-to-server communication, high availability clustering, security, well, all of those things are going to require some sort of layer 2 connectivity, all right? And in a lot of instances, layer 2 functionality has to extend beyond even a single data center, particularly when a campus framework extends beyond its predefined or kind of initially designed geography, right? So we might have these long distance data centers and so on. So what we're going to take a look at in this lesson is how we connect those data centers and what requirements and what solutions exist for that, right? So we'll talk very briefly about the need to have these data center interconnections. We'll identify IP address mobility problems that rise from having to have this interconnection. All right. We'll talk about dark fiber DCI topologies, which is very common. E over MPLS data center interconnections, VPLS data center interconnections, maybe layer 2 DCI caveats, right? What are some of the things that we have to consider when we're connecting these data centers over a layer 2 domain? We'll talk about OTV, which is also tested on quite a bit. And then we'll look at overlay networks and how overlay networks are affected by data center interconnects. So this is a very interesting a lesson here, and it's something that a lot of enterprises have to deal with on a regular basis. We may want to have geographically dispersed data centers for disaster avoidance or disaster recovery purposes, right? We don't want all of our resources to be physically located at one location, you know. For example, in Florida, maybe we are concerned about hurricanes. In California, we're concerned about earthquakes. So if we have data centers in both locations, if a hurricane hits, we don't have to worry about.
Why not put it in either one?
Yeah, put it in Nebraska,
Yeah.
the flyover state that nobody wants to go to. Yeah, Kansas probably fits in that category too. Brian, where are you from? I forgot. You're East Coast, I believe, right?
I'm up in Maine.
Maine, yeah. Yeah. Yeah, so, yeah, that's, yeah, you were with OTT, I think it was? Is that how we met?
That's how we met. Yeah, that was a long time ago.
That was a long time ago. You're not with them anymore, I'm sure.
Correct. I'm with Burns & McDonnell now.
Right. So, I remember some things. I don't remember all things. So this geographic dispersion enables optimization of applications through facility placement, right? We have workloads that get spread out across these data centers, and we utilize the capacity at both data centers. It's not just for disaster avoidance and disaster recovery, right? We can create these data centers, you know, to service clients in that geographical area, or to localize resources to that specific location. The problem that we have is that we need to be able to interconnect these data centers because they're ultimately providing the same resources, the same functions, the same compute, the same storage, etc. And there has to be some sort of communication between these data centers. To enable all the benefits of having these geographically dispersed data centers, we might have to have different types of communication required between the data centers. Virtual machines and IP address mobility, and, being able to move IP addresses back and forth between our data centers, move VMs between our data centers, that's going to require some sort of layer 2 data center interconnect, right? Because that's the only way that we're going to get that mobility with the VMs and with the IP addresses. Transaction replication of database clusters or application synchronization or application clusters themselves, they're going to require some sort of layer 3 data center interconnect, right? Storage replication, those requirements are going to differ from our VM and IP address mobility requirements and our transactional application replication requirements, right? It depends on the storage protocol that you're using, right? Fiber channel, for example, is going to require some sort of layer 1 DCI, so we're going to have some sort of fiber optic connection. Fiber channel over Ethernet doesn't necessarily need a physical layer DCI. It's probably going to need some sort of layer 2 DCI. iSCSI is going to need some sort of layer 3 DCI, and so on. So we have different requirements that drive these different needs for these data center interconnects, and the DCI design or the DCI methodology that you use will depend on what those driving requirements are, right? A layer 2 DCI. That's going to enable simple VM and IP address mobility. And we see a figure here that kind of describes that, right? We have a virtual server at site A in our data center. It has an IP address of 203.0.113.100. That's our public IP. Traffic leaves the local VLAN through the 203.0.113.1 gateway, and it gets forwarded through the core and out to the internet, right? We want to have that functionality, or the ability to migrate that VM to the other site. But when I try to migrate that VM to the other site, I have to keep the IP address. It's still going to belong to the same VLAN, but the gateway remains at site A. The IP network it belongs to is still advertised into the internet from site A, so that VLAN traffic has to be forwarded from site B across that layer 2 data center interconnect to site A, and then it gets rerouted to the internet, from site A. Without a layer 2 data center interconnect, that would be practically impossible, right? Well, it would be impossible. But what happens if that interconnect fails, right? How do I get that traffic from that site B VM over to site A? We know that the VM's default gateway is no longer reachable, all right? So we can use something like first hop redundancy protocols. The default gateway can exist on both sites, but then we run into the problem of the return traffic. What happens with the return traffic? BGP is still advertising the subnet from site A. So some of the servers from the same subnet could still be running at site A. So BGP is going to advertise that same network, but in this case, it's going to advertise it from site B. All right. If I'm advertising the same network from site A and site B, then I have a split brain issue, where some clients are going out of site B, some clients are going out of site A, but they kind of look the same, and there can be some confusion in routing in that case. All right. The servers from different data centers serve the content from different parts of the internet, but they're not really synchronizing with each other while that data center interconnect is down. So we could get some inconsistencies and data corruption in that case. And that would be a concern, right? There's another issue that occurs when we do our VM migration, and we see that in this diagram here. We have two VMs that have their default gateways in a different data center, right? When the VM at site B is communicating with a VM at site A, the traffic goes from site B through that DCI connection to site A to its default gateway. Then the default gateway forwards the traffic back through the DCI to site B based on the basic routing table entry. So the VLAN 20's default gateway at site B accepts the traffic, and then based on the CAM table, it sends that traffic through VLAN 20 back to the server on site A. All right? So this is a pretty bad scenario, right? Traffic has to traverse the DCI 3 times before it actually reaches its destination host. By the way, this is called the traffic trombone. Yesterday we talked about hairpinning, right, where traffic goes in and goes back out. Now we're doing this 3 times, so now they call this a traffic trombone. It's maybe a term that you haven't seen before, okay? So there are definitely concerns, all right, when we're doing these data center interconnects, particularly at layer 2. You know, and hopefully we'll see how we address some of these issues later on in this chapter, all right? It may not be a good idea in general, right? We may not want to create this high availability server cluster with VM mobility across multiple data centers, right? We should maybe utilize a second data center that has maybe a DRC instead, right? Disaster Recovery Center, as opposed to just using these VMs, right? It depends, right? It depends on what your overall architecture is, and really what your goal is, right? But you know, what the main thing that we're trying to look at here are some of the things that you have to consider when you're using these data center interconnects. All right. The issue with IP mobility is it's a complex problem, right? It's not an easy issue to solve, right? As the IP addresses really express 2 pieces of information in a single site. The device identity, of course, which is its unique identity in the network, and the device position in the network, all right? So it is definitely a challenge. It's definitely a challenge. Something to keep in mind. The next option that we have is what we call a dark fiber DCI. And we're actually going to take a look at a case study here where we have this dark fiber DWDM circuit between site A and site B. Because we're talking about fiber specifically, dark fiber is considered to be a layer 1 service, right? It's a physical layer entity, which means it's a physical layer service, right? It's really popular among a lot of customers today because the transports are available now. They didn't used to be as readily available as they are today, particularly between major metropolitan areas, right? But the nice thing about having this layer 1 type of service is it's going to allow the transport of lots and lots of type of traffic. We can run native Ethernet, we can run IP traffic, MPLS traffic, SAN traffic. The downside, though, is it's expensive, right? Especially as you add more and more sites, or, you know, based on the geographical location of the sites, it could be expensive as well. all right? So
And
dark
this,
fiber,
and also the distance as well, because there's a limitation.
absolutely, absolutely. You're not going to get dark fiber from Florida to Los Angeles, right? It's not possible. All right. It's depicted in the diagram here. Dark fiber is typically deployed on a DWDM network, and that's going to allow us to span our layer 2 Ethernet over a metropolitan area network. We could potentially go up to maybe 100 kilometers. Obviously, that would be extremely expensive, but it is going to provide that layer 2 data center interconnect for us. Okay. So the company in this case has 2 data centers. We need to establish a point-to-point DCI, and we've decided that the dark fiber DWDM link is what we're going to use. It's available between the 2 sites, and that's going to allow us to initiate multiple layer 2 connections. So the question that we have to ask ourselves then is which data center layers should that DCI interconnect to, and how should they be connected? All right. By the way, that term dark fiber actually refers to the fiber capacity that's installed, but not in use. In other words, it's not lit up, right? So it's available for lease or it's available for use. There might be fiber pairs or fiber strands that are being used within the bundle, but there might be these dark fiber strands that aren't lit up and they can be used, all right?
And now they have different names, like Express Route and Direct Connect over the cloud.
Correct. I don't think we'll get into those details in this lesson, but yeah, there are obviously some subcategories that exist as well. All right. DWDM, I did a sonnet and it was a class in England for the Air Force I did talking about DWDM and sonnet and interconnecting, because that's what the Air Force uses to interconnect their sites. And it's an interesting concept, right? DWDM is a technology that multiplexes a lot of OC signals, right, optical carrier signals, into a single fiber by using different wavelengths of light, right? Dense wave division multiplexing is what it stands for. So it gives you that the access to the media layer with lots of point-to-point physical layers, but each is built or facilitated on a different wavelength of that optical link. So lots of frequencies of light, all right? Okay, so let's continue with our little case study here, all right? The question I had asked previously was, well, where do we connect this to? And typically it's going to be connected to the aggregation layer. We're going to connect one aggregation layer, in this case the switch at site A, with the aggregation layer on the right data center to a switch at site B, and the other aggregation switches at site A with the other aggregation switches at site B. So we can have multiple connections. To exclude any layer 2 loops, we're going to bundle those links together using multi-chassis ether channel. We're going to join the aggregation switches on both sides with some sort of VSS configuration or VPC configuration, and then that's going to give us that high bandwidth, high redundant connection end-to-end with a fully redundant layer 2 network without the need for things like spanning tree or other technologies, right? We should always keep spanning tree enabled. That always needs to be there as kind of a last resort. And we're going to use other technologies like UDLD and whatnot to protect from having loops in the network. But the idea is that we're getting that aggregated link between the data centers.
Yeah, I read somewhere that spanning tree was used as a last resort in case of user misconfiguration.
Mm-hmm. User misconfiguration, failure, hardware failure, whatever, maybe the ether channel for some reason doesn't, the interfaces operate independently for some reason or another. So we definitely want to have it running still,
Even though you connect the data centers with the VPC?
Yeah, even if you have that, you still want spanning tree running in the background.
Okay.
In that case, it's not necessarily going to be used, right? We're not going to be disabling any links. We're not going to be disabling any connections because all the connections are bonded together. But what happens if something is misconfigured, like you said, or what happens if something fails for some reason? You still want to have that loop avoidance in there. All right. The number of data centers that we need to increase can also increase, right? In this particular case study, we have 4 remote data centers interconnected using this DWDM ring, all right? So what DWDM provides in this concept is a media layer to give us those various point-to-point physical layer links. But how do we connect the 4 data centers in a loop-free topology, right? What do we do that allows us to connect those data centers in a loop-free topology? What we need to do is we need to create this logical star configuration, right? In other words, make the data centers look like they're connected to a core. And that's what we see on the next slide here. Maybe if I can get over there, all right? So if I can create this logical star topology, that's going to provide us that loop-free interconnection for all of our data centers. We establish a layer 2 core, and then we have these redundant switches with VPCs and VSSs. That's going to allow our MEC connections between the aggregation layers and this layer 2 core. All right. Now, obviously, the layer 2 core is not really in the center there. It's not its own data center. It's not this virtual entity that somehow hovers in between all these data centers. It is placed at one of the existing sites. All right, fair enough. But where will we place that redundant layer 2 core? We want to be able to have the best scalability, the best redundancy, the lowest latency. So now we have the challenge of where do we place this core? All right. Well, actually, we don't place it in a single location. We spread the layer 2 core across different sites. Again, using VPC to allow our multi-ether or multi-chassis ether channel configuration. All right. And that's what we see here, right? And this is a critical design point, actually, because if we spread physical switches that comprise that layer 2 core into different remote sites, that's what's going to give us that high availability. And then we establish a logical point-to-point connection between those layer 2 core switches using the DWDM, and we bundle them together using a VPC or a VSS. Now we're really getting into some advanced design concepts. I mean, we're not looking at them specifically and looking at the configurations, et cetera, but we are seeing some of these more advanced design concepts, right? The logical point-to-point connections, they're laid out to produce this virtual star topology with that layer 2 core as the hub and the aggregation pairs as the spokes, right? For example, I mean, you can kind of see it in the diagram here, right? One of the aggregation switches is at site A. That's going to be connected to the layer 2 core A switch using a local link. The other aggregation switch at site A is connected to the layer 2 core B switch at site B using one of the available DWDM point-to-point links. By the way, those DWDM point-to-point links, how are they created? Are we talking about using a physical fiber connection? No. We're talking about using a wavelength, right? Creating this virtual point-to-point channel. And then, of course, that information gets multiplexed and so on. all right, which is why it's called dense wave division multiplexing, right? So we create these connections, and the aggregation switch at site A gets connected to the layer 2 core B switch at site B using one of those point-to-point links that was created between site A, site B, and so on, okay? We would also configure site B, C, and D kind of in the same way. Applying the same interconnection methodology to all my sites gives me that flexible design. What's the limitation, though? There is a limitation. All right? It's the number of wavelengths that are available in the DWDM ring. That's going to limit the maximum number of uplinks that are available from the layer 2 core in my topology. The next DCI concept that we're going to talk about is a Pseudowire DCI. All right, we know generally speaking what a Pseudowire is. Pseudowire is using a service provider MPLS network to create this virtual physical connection between between different locations. This is probably a more preferred method, even though it doesn't give us as much flexibility as the DWDM design does with the dark fiber. But the problem with dark fiber is it's expensive, right? And also it's not as widely available, right? It has range limits. There's a whole bunch of different limitations to dark fiber. So service providers offer kind of this more practical option, which addresses all of those different concerns, right? Range limits, expense, availability, and so on. And it's called a Pseudowire. A Pseudowire is an emulation of a point-to-point connection over some sort of packet switch network. That's a fancy way of describing what we already talked about when we talked about everything over MPLS, right? Everything over MPLS is a typical service provider Pseudowire service that offers this point-to-point Ethernet connection, right? In that case, any ingress layer 2 traffic at one location is transported and then delivered to the remote location as it is, right? It doesn't matter if it's a control packet. It doesn't matter if it's a regular data packet, because this is literally a virtual physical wire, all right? When we're interconnecting two data centers, it is pretty typical to bundle two Ethernet pseudowires so that we disable spanning tree between the locations and then contain whatever spanning tree topology changes or spanning tree algorithm process we have to run within the location itself, right? Again, that's going to give us an aggregate bandwidth. It's going to give us redundancy and so on. We talked about VPLS, right? VPLS is kind of a pseudo-wire function, the virtual private LAN service. That's a class of VPN that supports the connection of different sites in a single bridged domain over this managed MPLS network, all right? It's basically just an Ethernet interface to the customer. The service provider network is acting like a LAN switch. And we talked about that when we went through the MPLS discussion, right? So we can create now, excuse me, VSSs and VPC pairs of switches over that VPLS network to emulate, you know, or to utilize Ether channel and so on. The problem that we have here, okay, because VSS and VPC pairs of switches connect to that VPLS network, and that VPLS network is emulating essentially an IEEE Ethernet bridge, Ether channel specifically is not available, right? So we can see layer 2 loops in the network, and that has to be solved with the use of spanning tree. So we get this introduction of the spanning tree protocol in our DCI, but it doesn't only block some of the redundant links. It might also extend that spanning tree domain across the data center interconnect. So we're going to get floods of BPDUs across the DCI, and that's going to obviously result in bridge forwarding, table flushes, and so on. So we have to be concerned with that. There is another solution. It's called a VPLS, which is the Advanced Virtual Private LAN Service, and this is a Cisco extension to this VPLS solution. And what a VPLS does is it extends the multi-chassis Ethernet channel concept over that VPLS network. So it's actually going to allow us to use MEC on the redundant links across the VPLS as long as both of the switches at the customer sites are in a VPC or a VSS, which would solve that spanning tree problem, right? So that is another piece of technology that allows us to enhance the service that we're running across these DCIs. There is another option, any transport over MPLS or over GRE, all right? That is our ATOMO, I forget what the acronym is. It's, I think it's ATOMOGRE, I believe that's what it is, right? Any transport over MPLS or over GRE. If the service provider doesn't provide Layer 2 VPN services, or in the case where DCI needs to be established over an existing IP core, like everything over MPLS or VPLS, or in the case where everything over MPLS or VPLS is not an option, right? We have a problem because now we have to create this overlay to logically interconnect these enterprise devices in our different data centers. We can't run this EO-MPLS or VPLS function because it's an IP core, right? Which means it's participating in routing is basically what it means, right? Or, you know, it's some routed core network. You get what I'm saying? VPLS and everything over MPLS is a Layer 2 concept, right? If it's an IP routed core, we can't do that, all right? So what do? Well, we use GRE tunnels, okay? The EO-MPLS or VPLS traffic that we have to create simply gets encapsulated inside of the GRE tunnel. That's going to allow all my Layer 2 traffic to flow over that IP core, and this is called the ATOMOGRE solution, right? Any transport over MPLS or and GRE, all right? Basically, what it ends up being then is an identical deployment over a service provider MPLS network. By using this design method, we're allowing the enterprise to build that EO-MPLS point-to-point connection across the link from site to site, but these connections are being transported over that existing IP routed core. All right? We don't necessarily need to deploy MPLS in the core network to support this either. All right? If the enterprise requirements state that we want to interconnect multiple sites in a multi-point fashion, as opposed to a point-to-point fashion, we know that VPLS is generally the recommended technology, right? Because VPLS simulates this IEEE bridge, and it's a multi-point design scenario. All right. Just like EO-MPLS, the VPLS stuff, that's a technical term, can be transmitted or transported over this IP backbone or this IP core using GRE tunnels. Okay. As always, when we're interconnecting our data centers, the best practice is to bundle those pseudowires to disable spanning tree between the locations and then contain the spanning tree topology changes inside the data center locations themselves. All right? There are some considerations that you have to take into account when you're dealing with Layer 2 DCI. We know that existing mechanisms for the extension of Layer 2 connectivity is a lot less optimal if we're trying to address connectivity and independence requirements. And there are some challenges that we run into, and we see those challenges in this slide here, right? The first one we see is this data plane learning and forwarding challenge, right? The extension of our Layer 2 domain across multiple data centers can actually cause the data centers to share failures, right? Normally, those failures would have been isolated, but if you're interconnecting your data centers over an IP network. But they can actually propagate pretty freely over a Layer 2 flood domain because Layer 2 is a lot less forgiving than a routed network, right? So that's something to keep in mind when you're using a Layer 2 DCI. The Layer 2 addressing is flat. It's non-hierarchical, right? MAC addresses are used to identify our hosts, not IP addresses. So a MAC address doesn't necessarily point to a device's physical location. And I've always taught students this in the past. It's a lot more difficult to troubleshoot large Layer 2 topologies than an IP domain or a routed topology, right? Also, Layer 2 addressing is non-summarizable, all right? So we get this really large address table growth for all the devices in our Layer 2 domain. An additional thing to consider. Spanning tree, all right? If we have multi-home sites, we know that we have to have spanning tree running across the DCI core to prevent routing loops, right? Not routing loops, Layer 2 loops, all right? And if I'm not bundling or bonding links together, redundant links get blocked, and we waste the bandwidth for those redundant links. So it's a similar concern that we always have in any Layer 2 domain, all right? Lastly, complex operation. I don't know if you guys have picked this up over the last few days. We've been talking about these different types of VPNs and so on, but Layer 2 VPNs allow us to extend Layer 2 connectivity between data centers, but that's going to mean that we're going to have to implement a lot of pretty complex protocols. We're going to have distributed provisioning, it is based on what we talked about with the first few problems that we see here, it becomes operationally intensive from a hierarchical scaling model, right? The flat addressing, the non-hierarchical addressing, the data plane learning and flooding, and so on. A simple overlay protocol that has built-in capabilities of point-to-cloud provisioning is also extremely important, and it's necessary to reduce the cost of, provisioning this type of Layer 2 VPN connectivity. All right. That doesn't mean that with all these caveats or with all these concerns that there's not a place for it, right? And there's definitely a place for it, but just wanted to point out some of those potential issues that you might see. All right, we talked about ATOM, OGRE, any transport over MPLS and GRE. That's a solution that requires the establishment of some intermediate layers of communication, namely MPLS, okay? Which is, again, going to add another level of complexity into the network design. OTV, right? OTV, which is our overlay transport virtualization, is going to provide us a different option, right? It's actually an IP-based function that's designed to provide layer 2 extension capabilities over any transport infrastructure. It could be a layer 2 transport, it could be a layer 3 transport, MPLS, et cetera, et cetera. So we can extend or interconnect our data centers using this OTV function. The only requirement that we have from the transport infrastructure is to provide some sort of IP connectivity between our remote data center sites, all right? On top of that, OTV provides an overlay that enables layer 2 connectivity between separate layer 2 domains. And it actually keeps these domains independent. So it preserves that fault isolation that we didn't have with a layer 2 DCI. It gives us that resiliency, load balancing benefits, everything that we would expect to get from an IP-based interconnection. We're going to get that with OTV, all right? So it's, and you can see that it does provide a lot of functionality, right? Now, the caveats, of course, we see that listed here on the slide. It does MAC routing, right? The control plane protocol that's used to exchange MAC reachability. So we don't have data plane flooding capabilities. We'll talk about that a little bit later on. The nice thing is that we don't have pseudowires, we don't have to have MPLS, we don't have to have spanning tree, and we don't have to have ARP caching, multicast optimization, and so on. So there are a lot of benefits that OTV gives us over our layer 2 DCI that we talked about previously. All right, and we're going to talk about a lot of these different benefits as we go through the rest of this lesson here. Okay, we're just about done with this lesson, and then we'll take a break and we'll move on to the next one. All right. So what OTV does is it introduces the concept of dynamic encapsulation for our layer 2 flows that need to be sent between our locations, right? Every Ethernet frame, layer 2 data, every Ethernet frame that we have to generate between our locations gets individually encapsulated into an IP packet. And then it gets delivered across the transport network. The fact that we're creating this dynamic encapsulation eliminates the need to establish pseudowires between our data center location. We can use an IP transport as our core network, and but we still get the benefits of this layer 2 process, right? We still get the benefits of this layer 2 connectivity, okay? And that's what we're seeing in this diagram here. We've got an IP core network, and Ethernet frames get encapsulated directly inside of our IP packets. So we don't have to have any intermediate layers to allow this connectivity. All right. Now, I had mentioned in one of the previous slides, in fact, it was this slide here, this concept of MAC routing. So let's go into what that MAC routing concept represents. This is a diagram that's supposed to describe this MAC routing. It doesn't do a very good job of it. I mean, we see the layer 2 and the layer 3 separation, but it doesn't really give you a whole lot of detail about what this MAC routing is. So let's talk about it. All right. The MAC routing function in OTV, it is a control plane function, a control plane protocol, and it is used to exchange MAC reachability information between our network devices, which gives us LAN extension across the IP core, right? This is a very, very different process, right? A significant shift from the layer 2 switching that leverages what we call data plane learning, right? And one of the downsides to that standard data plane learning process is the flooding, right? The flooding of layer 2 traffic across the infrastructure. So this MAC routing function eliminates that. It eliminates that, or at least it limits the flooding of layer 2 traffic across our transport. All right? Let me explain how. If a destination MAC address information or the destination MAC information is unknown, we know that in a standard layer 2 domain, what's going to happen with that? We're going to flood that information out of every interface except for the interface it came in on, and that's going to take up valuable resources. If, in the case of MAC routing, if the MAC address information is unknown, much like a router does, that traffic gets dropped. It doesn't get flooded. That's going to prevent the waste of bandwidth across our WAN link. All right? OTV encapsulation is performed on the OTV edge devices. Those are going to be positioned at the edge of our layer 2 domain. Okay, so let's say I have an OTV device at the edge of site A. When that OTV device at the edge of site A learns a new MAC address, in the case of this diagram here, it is 000000112223. Okay, so it learns this new MAC address on its internal interface, gig 01. Gig 0. That's right, doesn't have a 1. So right here, gig 0. We're learning about that, on this interface right here, okay? And we're learning that through, you good to go?
I think it's the tunnel aggregation and the packets per second for the heaven.
Oh, the VPN?
I did some reading and it looks like.
So we learned that MAC address 112233 on the internal interface of gig 0. That was done, by the way, through just traditional MAC learning, right? Remember, the OTV component only runs at the edge of the network. It doesn't run inside the network. What happens, though, in this case is the OTV edge device creates an OTV update message, and that's going to contain the information about the MAC address. It's going to send it across the IP network to all the other OTV edge devices. So MAC reachability information gets imported in the OTV edge device CAM table. The only difference with a traditional CAM entry is that instead of being associated with a physical interface, it's going to be associated with the originating OTV edge device information. Okay? So if I receive a layer 2 frame at the OTV edge device, the layer 2 lookup gets performed. If the MAC information in the CAM points to an IP address of an OTV edge device rather than a physical interface, the Ethernet frame gets encapsulated inside of an IP packet. It gets sent over the IP network to the remote OTP edge device. That encapsulation gets removed, right? Once that encapsulation is removed, then the frame gets switched natively using regular MAC address and regular switching methods. Okay. In addition to providing this functionality, right? By the way, the protocol, everybody's always talking about where is ISIS ever used, right? On the test, yeah. Actually, OTV uses ISIS as its control plane protocol. It was based, it was because the protocol itself was originally designed to to carry MAC address information. That's just a little caveat. You want to impress a girl at a party or something, you can bring that up. But, you know, depends on the, yeah, exactly. OTV also provides built-in multi-homing capabilities, automatic failover detection, so we can get this high availability in our solution. We can have 2 or more devices that can leverage, that we can have in each data center to provide this LAN extension functionality without creating a loop, and that's really, really important, right? OTV doesn't require a spanning tree protocol across the DCI because it is based on a control plane routing protocol, right? There's also some other optimizations that OTV provides. We can snoop ARP replies. We can look at single IP to MAC bindings to remote nodes. And then that's going to reduce the amount of ARP traffic or ARP broadcasts that are required. We can use multicast to help make sure that we have optimal replication of multicast or broadcast traffic or signaling traffic. So it's multicast aware, in other words. It's a really, really useful tool. And it's one of the most common methods of extending this data center interconnect across multiple data centers. It's only supported on the Nexus products, Nexus 7000 and 9000, not on the 5000. Also on the ASRs, the 1000 as well. Okay. The last thing we'll talk about is the overlay network, right? We've been talking about overlay networks a couple of different times. We know what an overlay network is, and there are many, many different types, but the most common is the VXLAN, at least in a Cisco world. And we know generally what the overlay network does, right? It allows us to span our layer 2 network across an underlying IP network, all right? Question is, can we use this technology to provide a layer 2 DCI, right? It wasn't really designed for that, right? VXLAN was actually designed to address other problems of extending communication across the layer 3 transport within the data center. So it's actually designed to run within a single data center. The problem with VXLAN is that it doesn't have the control plane functions. It relies on standard layer 2 data plane address learning with unicast flooding and so on. So due to that MAC in IP encapsulation, VXLAN also requires a 1600 byte MTU. Remember, we have that 24-bit header that gets added to the VXLAN data. You know, and supporting jumbo frames inside of the data center, that's not that difficult. In fact, it's readily available. We can do that all the time. But that may not always be the case on IP connections between our data centers. So I would say, based on all those things, that VXLAN is not really considered a DCI technology. You should look at OTV or dark fiber or some other option. Okay, just something to think, because you know, you think about VXLAN, you think, wow, that's a layer 2 extension across a layer 3 domain. That sounds like what DCI does, right? But there's obviously those limitations. So these data center interconnects, we have our layer 2 for IP mobility and VM mobility. If we're trying to do any kind of transaction replication, database replication, we're going to use a layer 3 transport. Storage replication can, of course, go across 1, 2, or 3, depending on the type of storage application that you're using. IP address mobility with a layer 2 DCI has a couple of different issues that we have to deal with: split brain functionality as well as traffic tromboning. Dark fiber is great, but it's expensive. We have limits in range and availability, all right? So if we want to run over a service provider VPN, either everything over MPLS or VPLS, which provides our multi-site functionality, we have to run other DCI flavors, right? And we can use ATO-MO-GRE, everything over MPLS or VPLS over GRE with an IP core, simulating the pseudowire connectivity over a layer 3 domain. And then finally, we talked about OTV, which is really the preferred DCI function. And I would say 99% of the time, that's what's going to happen. That's what we're going to be using for our data center interconnects is the OTV function. Okay? So that is the end of that lesson.